is a project for the project.
Yeah, I mean, so it really depends on the class. So, like my classes, typically I give so many homework assignments where you effectively have a bunch of projects that the exam's the only way I can tell whether or not you like have some level of competency. I don't necessarily grade them overly difficult. You can usually tell pretty quickly whether or not this person likely either does their homework themselves or gets enough out of their homework or is riding somebody else's coattails, turning in somebody else's work, has a friend who's just doing all the work for them, whatever it is. So you kind of catch them on the exams as to whether or not they got out of the class what they should have gotten out of the class. Doesn't matter to me. I mean, I'm not going to sit there and try to catch you cheating, but you're only hurting yourself because you're not going to learn this stuff. I get paid either way, whether you do your own homework or not. But
You say you can't just go and check or like things or whatever, and like copy, like put all your like jobs.
sure you can.
There, be like, hey, Ian, programming.
Yeah, we've seen plenty of students come out and go and get jobs that way, and they get fired. 2 months later. Okay, what was that referencing? Right. BL before Littman. Yeah, that was in 2006. I came here. Okay, so let's see. So we talked about. So today you were having a paper for comparing Java, C, C++. Let's spend 2 or 3 minutes. What are the highlights? Anything stand out to you that we didn't talk about in class in terms of the differences in those languages? Okay. I think we kind of covered that in the class. They all come from C. C++ is the object-oriented version of it. Java is kind of the C++++. Anything you came across in the stuff? Go ahead. Yep. Let's see, where is that? Yeah, so here's that Java source. So Java gets compiled into Java bytecode, which runs through the Java virtual machine, which then kind of gets interpreted for the CPU because that Java virtual machine that's a computer written in software that knows how to run Java bytecode assembly, and it's having to flip that into effectively native assembly for the CPU, although it's the JVM that's already in native assembly. It just runs that program. But yeah, so Java is both a compiled and I would say a quasi-interpreted language because you're really going from low-level language to low-level language and not even that. So it's not going to be the same level of slowness as some other purely interpreted languages go because you're not having to go from high level to a low level, but it does still have an interpreted step. All right, anything else?
This went a little like over my head when I was doing research, but it seemed like C++ uses like header files instead of importing, which is what Java uses.
Mm-hmm.
I don't exactly know the differences between those, but it sounded like C++ doesn't use importing stuff.
Well, sort of. So let's kind of, and we're going to be talking about that quite a bit. We might even get into it. Actually, probably will get into it today. So header files versus importing. So in Java, so we might say in Java, we might import something like java.util.random, something like that, right? What are we actually doing there? If we're importing java.util.random, what's happening? Go ahead. Okay, so somebody wrote a library. Really, it's a class named random. that we want access to in our program. The random class contains both the, well, contains the entire implementation of the random logic. In C++, we might hashtag include instead of import. Let's call it hashtag include. Maybe something like stdlib.h. All right. So in this case, someone wrote a program likely called standard lib.c and also wrote a header file called standard lib.h, which contains which acts, or let's see, looks like an interface in Java. Remember interfaces in Java? So they're kind of like classes, but instead of them having an implementation in it, they are just kind of a list of the methods that you must write in order to follow along, or in order to implement that interface. So we would call, so header files are like interfaces in Java. .c files are the actual implementation of what is in the header file. In Java, a class behaves as both the header file and the implementation. All right, so effectively having two files instead of one file is the main difference there. They're ultimately accomplishing the same thing. What was the question here?
So why do we include the H file versus the C file?
Because the H file says these are the things that are available to me. During compiling.
So when it's compiling, it reads the H file and includes stuff in the C file?
Correct. Well, the C file gets compiled. During compiling, it brings in all the libraries from the header, all they would be called function prototypes. And when we get into this, I'll give an example. But effectively, this is for the compiler's benefit. When the compiler goes through your code, it finds out all your external entities that are available to you that you included up top. So that when you start hitting things, when the compiler starts hitting lines of code that you wrote, and you start referencing something from one of those libraries, it says, oh, I know what you're talking about because you had prototyped that up top. But instead of us going and writing individual lines for the prototype, we just brought in header files. Some of those header files might be ones we wrote. We're going to write plenty of them in here. Other ones might be ones that like standard IO, IO stream, things like that. But it's for the compiler's benefit. Go ahead.
So when you're writing like a C or C++ code and you have a header file and you have the other file, so do you reference your own header file for your own?
Yeah, and you're going to see that by example. We're going to, I mean, that's going to happen literally on a daily basis when we jump into C here, yeah. C++ here.
I thought you just wait for that.
Yeah, and we're going to be looking at it today. All right, so really to get to this point about header files versus importing, they both accomplish the same thing. Java's perspective would be that, oh, we made things better by having header file, by getting rid of header files and instead just having everything inside of the single file. Now, I might argue that that actually isn't better. What if you have a really large program and you have to scroll through 4,000 lines of code to find stuff? Now, a lot of our modern IDEs let you hit the little arrow thing and it kind of like minimizes a function. So in the end, you effectively just have a list of functions that are in there, which effectively looks like a header file. Okay, so IDEs will allow you to adapt Java to accomplish this. Now, but Java wasn't completely at a loss. Java said, you know what? Rather than you having to have 2 physical files for every single thing you write, you actually don't have to. It's just that's the kind of best practices for writing C++ and C code, is to have 2 physical files, the header file and then also the implementation file. Java said, rather than having 2 files, we're just going to have 1 file, but we're going to include a technology called Java doc, where if you want to put directives before your functions and then run the Java doc command, it'll generate an HTML file that has effectively the contents of your header file, what would have been the contents of our header file. I like header files from the perspective of I can just glance at a header file and see here's all the abilities of this thing, as opposed to having to look at the 4 million lines of implementation that goes with those abilities. All right. So I maybe wouldn't say that there's a drastic pro and con to it. Java does save you from having to create 2 files every single time you want to write something, I suppose. Go ahead.
You see that a lot of these header files are like C++, they come with the like C++.
Yeah, but same thing. I mean, Java.util.random comes with Java, and other times we've written our own, like we've created a person class, right? We didn't have to include it because as long as it was in the same directory, it just found it. But that would be the same type of thing where in C++, we would have to include it. Just that's part of how it. Well, you would if you use non-standard libraries, but typically with they're all available. Just like when you have the Java runtime environment installed on a computer, the core Java abilities are there. Same thing's true here. Okay. All right. Anything else of interest from the paper?
They're more different than I thought they were.
Okay.
Just when you not know anything about like C or C++, not really know about C++. But like I said, I'm like for a while out there, very familiar with the fact that like C isn't really understanding, but I didn't realize that.
Really? Isn't it in our notes?
It's in our notes. I didn't realize that until like we talked about it in our class. Like, that's when I learned about that.
Oh, okay, I got you.
Until we learned about that.
Sure.
Yeah, no, it is in the notes. Like,
I got you. Okay, so let's start looking at some of this stuff. So we're going to do this in Visual Studio Code. Just going to relaunch it. Where do I get that weird blue screen? All right, so we did hide this. All right, so we did run this last time. So we've gotten into this a little bit. Okay, so notice here that what we're doing, so this is the C++ version of the C Hello World program. So in C, we're including standard IO header file. This is something that's built into built into the operating system. All right, to do standard input and output on, in this case, Linux. We have our main method. We use printf to write stuff out to the screen, so on and so forth. Now, we can use standard IO in C++, but one of the things C++ introduced to us is streams. So instead of using standard IO, we typically use IOStream in C. And notice that we're actually importing the IOStream namespace here, including the namespace rather than a header file. just the difference between the C and C++ compiler. And then more modernly, C++ has a global, well, has a standard namespace that it kind of sucks all the common elements that you might use in a C++ program into. So if you don't want to have to write, I think last time I showed you, if you leave this using namespace thing out, this guy's going to not be a fan. It doesn't know about cout anymore. I can reference it and say, well, standard cout is part of the standard namespace. So I actually would use a syntax like this to make it work. All right. We're not going to do that. We're usually going to include the namespace, but you're actually going to see this syntax pretty quickly here once we start writing classes. Okay. All right. So let's go and let's look at something called a struct first. All right. So a struct in C, and it also is in C++. This is kind of like a dictionary. Remember from Python, we had dictionaries, collection of name value pairs, and those things exist in Java as well. We didn't really use it in Java, but Java has a thing called a hash map and some other things like that that effectively allow you to accomplish the job of a dictionary, where you have a single variable with a bunch of name value pairs. Similarly, in Java, you could have just created a class and put a bunch of fields in there, and that could have been your collection of name value pairs. Okay, but when we go back in time a little bit, in fact, that's kind of one of the things is Java does not support the idea of a struct. So let's look at a struct here. So I'm going to go ahead and I'm going to define, I'm going to say struct person. And this guy's going to have a char pointer f name and a char pointer l name. Let's do something like that. And then we'll go ahead and define a variable. So we'll say struct person p1, struct person p2, p1.fname is equal to Mike, p1.lname is equal to Litman, p2.fname is equal to Dave, p2.lname is equal to Smith. Then if we want to write some stuff out here, we'll just go ahead and we'll output p1.fname.
I have a question.
Yep.
Does lname also need to be a char pointer?
It does. Thank you. All right, so let's see this run first. All right, so I've created, so effectively what I've done here is I've almost created like a, think of it like the predecessor to a class in Java. Go ahead. Yep. Mm-hmm. This guy's a string. Oh, yeah. It kicks it down a line. It's the same thing as doing that. Putting a \n at the end of it. Yep. All right, so effectively here, what I'm doing is I'm saying, look, I want to create my own little variable type. And structs allow us, it's a structure. That's what a struct stands for. It's a structure. It allows me to create a data structure for holding pieces of information. It does not let me embed functions like a class does in Java. Okay, so remember, structs came from C. These are predecessors to object-oriented languages. All right, so I'm defining a concept here. And then I'm going to go ahead and create a couple of variables of that type. So I'm going to create a person called P1 and another person called P2. Now, these guys do not have constructors like classes. So in order to fill them up with information, I have to do this, P1.FName, P1.LName, so on and so forth. All right, so let's go ahead and see this run first, then we'll talk about it a little bit more. Let's see, where did I put this stuff? This is parallels. All right, so we're going to go ahead and we're going to run G++, hello world CPP. It just gave me warnings, didn't it? String constant to char pointer. All right, that's stupid for my example. Let me. It wants me to create memory for this guy, which I don't really want to do yet. But I wanted to focus on pointers. All right, so there's my Mike Smith and there's your Bob hard-coded out. Realistically, let's just go back here into the code. If you were a C++ programmer in the early days of C++, you would not have had access to a variable type called string. That's something that is a much more recent inclusion into our code. Just to kind of give you the historical thing here, I think I need to include standard lib. So I'm going to say Malik's in standard lib. So something you can do from Linux. So I need to allocate some memory. Okay, that's I'm kind of connecting some dots here. Remember in Java, what was the keyword that allowed us to generate new memory? What was our real estate agent in Java? So in Java, I could have written something like, even though we typically define strings using the syntactic sugar for just saying string s equals Mike or something. In Java, I could have said string s is equal to new string Mike. I could have done that in Java, calling upon the constructor for strings using the new keyword. This would have gone out and gotten me brand new memory for storing one of these guys, and it would have put the value Mike inside that object. That make sense? The equivalent in C++ and C is I want to create a char pointer. Because remember, how are strings, so we're going to get into talking about memory here pretty quickly. You really can't talk about C and C++ without getting into the weeds with memory. Let's do it this way. How are strings stored? So if I have the string hello, that means somewhere, so let's say we have s is equal to hello. That means somewhere we have in memory a variable named s. I'm going to make up a memory location. So let's say that it happens to hold the value 100. All right, looks like this. I'm actually going to add one additional thing in here. Okay, so we're going to assume this is memory. This is bucket 0. This is bucket 1. This is bucket 2, 3, 4, 5. So those are our indexes of that. And we'll say this is memory address 100. How big is a char? So I'm walking through memory here. So the char primitive type in Java, here. How big is a char? So we're getting into the weeds here with memory. So remember when we first introduced the primitive types, I probably showed it to you the first time in 200, and we probably looked at it again in 250, where we had, remember all the primitive types, byte, short, int, long, char, float, double, Boolean in Java. How big is a char? How many bits do we have allocated for the char primitive type, let's say in Java? What do you think? Yeah, we got nothing? How big is a char? What is a char? Let's go that route. Go ahead. Huh? 1 bit? You think it's 1 bit? What is a char? Tell me everything you know about chars. What kind of values do chars hold? Go ahead. Okay, tell me about that. What do you mean they hold numbers? And what do those numbers correspond to? So like, can I say char C is equal to A? Is that a legal use of a char? So this isn't allowed. Go ahead. They all, both of you are right. This is allowed, right? I mean, don't overthink this. This isn't a trick question. In Java, I can create a variable of type char named C, and I can put an A in there, right? The question is, what is actually getting stored inside of C? What's getting stored in there is a number that corresponds to A where? Come on, people. Tell me about Unicode. What's Unicode? / ASCII. We would have talked about Unicode in 200. So in Unicode is a big file, the lookup table that has 65,536 unique characters it knows how to represent. The first 256 of which are the Ascii character set. After that, it has symbols from other languages and things like that. So in Java, chars are 16-bit values. And they're 16-bit unsigned integer values. That is 0 to 65,535. C and C++, these guys are 8-bit unsigned integer values, 0 to 255. The first 256 bits in ASCII well, the first 256 values in Unicode are identical to the ASCII character set, really extended ASCII. Original ASCII was only 128 characters. Then we had extended ASCII, which still made it very pro-English speaking. But Unicode it's a much more universal code for symbols from other languages, right? Okay, so to store a character in any programming language, computers like numbers, right? Computers like numbers. Human beings like letters. So when we think about the letter A or the letter B or the letter C, we can just remember that. In a computer, we have to go and look up some number to get the corresponding value to the A or the B or the C. So chars actually hold, as you said, numbers, but the reason we would use a char is because we mean to hold a character. And at runtime, that mapping occurs either on ASCII or on Unicode, okay? But from our perspective right now, a little bit kind of blindsided. We should have known. Most of that conversation, I think we should have known. That's okay. We're in COVID fog, COVID brain, right? So this would be something we would write in Java. We can also write this in C and C++. No harm, no foul. We have a char primitive type. We can give a variable name, whatever we want, equals, and then we need to give it a value that is the appropriate type for this. Okay? Now, because we gave it a literal char, so this guy would be called a char literal, where literals are hard-coded values in a language. So, for instance, all of you know about the number 2. Yeah, I'm not making any assumptions so far today. Okay, so we've all heard about the number 2. Got that guy? Okay, that's stored somewhere in your head. You didn't have to do any math stuff or anything like that to go look that up. Somewhere in your head, you have stored the literal value of 2, and nobody can change the definition of 2 for you, right? 2 is 2, always. Nobody can go in and remap 2 to a 9. Okay, 2 is a literal value. It's hard-coded, doesn't get anything lower level than that. So for a human being, so all of you, we've heard of the letter A, right? Okay, so now we're back on track. We're getting nods. Okay, so we've all heard of the letter A. That's hard-coded in your head too, just like a 2, correct? Computers have to do a mapping because, and most of you are in the 325 class this semester, right? Okay, so you're going to be talking about how stuff is actually stored inside the computer in there through these things called hardware registers. So hardware registers hold a bunch of bits, zeros and ones. So if we want to somehow represent an A under the hood in memory, I need to store a number that corresponds to an A. Okay? And that number is either found on the Ascii character set or the Unicode character set. Unicode is a superset of ASCII. From our perspective in here, we're pretty much using, numbers and letters from the English alphabet, punctuation from the English alphabet. So ASCII is good enough for us, but clearly other languages exist in the world, so we probably do need a larger character set in real life to represent programs that might have stuff from other languages. Okay, but The value for the letter A in ASCII is the same as the value for the letter of A in Unicode. The Unicode is a superset of ASCII. So this guy right here is a Char Literal. It's a hard-coded value. Humans know that as a Char Literal. A computer is going to say, ah, I need to map that to the corresponding value. So Char Literals in a computer, in terms of the way it stores it, is ultimately going to be a number. Make sense? Okay, good. Yeah, the compiler will do the conversion for you. All right. Well, but you can. So let's look at some examples of that. So I'm going to go back here and I'm just going to say char C is equal to an A. And let me just, well, I'll leave that stuff in there for right now. We'll use this last one here. So I'm going to go ahead and I'm going to print out C. And then I'm also going to print out the int version of C. So this will show us the ASCII value for C. So when I print out C here, C's type is char, correct? And because its type is char, when I go to print this out, C++ is going to do that lookup, and it's going to go and look up C, the integer that's stored inside of C, because as you pointed out, chars hold numbers, okay? But as Emily pointed out, ultimately we really want it to hold a character, okay? So since we've described this guy as being a char, when I go to print it out right here, it's going to do that lookup on the, because we're dealing with C and C++, which is a, frankly, actually, I'm not even positive. Since C++ has been updated significantly more recently, it might use Unicode now. I'm not positive about that. But certainly, historically, it would have used ASCII. All right? They're supersets of each other, or Unicode's a superset of ASCII, so it doesn't really matter. But it's going to go and look up whatever number is stored inside of this variable C on that chart, either the ASCII or the Unicode chart, and come back with an actual char that is going to display on the screen. That's what's happening on this line. So C++ will look up the number stored in C and get the char from ASCII. And this is no different. This isn't a new C++ concept. This is something that was true in Java. It was true in Python. Computers hold numbers. Make sense? All right, so anytime we want to start going into alphabets, we have to have some sort of mapping because computers hold numbers. All right, so this is going to print out the value stored in C after it maps it back to a char. So we'll print out an A. Now in this next line here, I'm saying, now I want to output, don't do the conversion. Give me the integer version of C. This will give me the ASCII value of whatever is stored inside of the variable C. I'm telling C++, don't do the conversion. Treat this as a number because it already holds a number. Make sense? So this will give me the ASCII value of an A. Forgot my semicolon there. So there's an A, and then there's the ASCII value of A. Now Unicode and ASCII have them in order. So if A is a 97, a lowercase a is a 97, that means a lowercase b is a 98. All right, so I can come in here and I can say int C2 is equal to 98. And I can come down here and I can do a C out char C2. And I can do a C out C2. So now I'm saying take the integer that lives inside of C2, map it on the ASCII table, which should give me a B because I put a 98 in there. So there's my B, and there's my 98. That makes sense? Okay, so that's how chars are stored. This is a truth in all programming languages. Go ahead. Oh, yeah. And it's not because of the languages themselves. It's because what computers know how to do. Computers know how to store numbers. Full stop. That's what they do. We've said for forever, right, that, oh, what language do computers understand? They understand zeros and ones, right? What do we use zeros and ones for? To represent numeric values, right? It's a counting system. So if we want to hold values that are more meaningful to human beings, we have to have some way of taking a number and having it correspond to literals that may be human beings, like the letter A, the letter B, the letter C, so on and so forth. Does that make sense? Okay. Now, this also then implies that we can do math with a char. So I can say something like for char, let's see, we'll call this alpha is equal to an A. Keep going as long as alpha is less than or equal to a Z, alpha plus plus. And we'll do C out alpha and del. So I'm using a for loop that's looping through all the letters in the alphabet because those guys hold numbers. And this will work in Java, this will work in Python. Python's actually a little bit weird because Python, you can get at the ASCII value with Python, but Python makes it a little bit more cryptic to get at it. There's a specific function that allows you to get at it and go vice versa. So it's possible in Python, you cannot do direct math with chars. You would have to use the function to, I think it's the ORD, the ORD function that will take a character and give you the numeric equivalent to do math. But this should work in C++, so this should ultimately print out the whole alphabet. All right, seeing that guy kind of work? All right, and again, none of this stuff we've talked about so far is something special to C++. All right, this is just how things are actually working under the hood. One of the things you're going to recognize a lot more this semester, especially with the two classes, 325 and in here, you're going to be dealing with memory a lot more. Okay, C++ forces you to do that. That's what we're talking about here. All right, so before I dive into a deeper problem here then, are there any questions about what I just did here with chars and that kind of stuff? So far, so good? All right. So a char in C++, you know what, actually, let's prove it to us. Let me give you a good answer. So C out size of char. I'm going to guess that a char in C++ is going to still be ASCII. So I think it's going to give me a 1 for 1 byte. But it might give me a 2 for 2 bytes. Yep, it's 1 byte. So my slide is correct. So in C++, chars are 8-bit unsigned integers. So they are mapped to the ASCII character set or extended ASCII character set, which has 256 unique values in it. All right. So that means that if I'm in, so that's how big a char is. And let's see, I was talking about strings right before that, right? Okay. So here's our string. So a char is 1 byte big in C++. So for this string, that means the H lives at 100, 101, 102, 103, 104, 105. Okay. This is memory address 100, memory address 101, memory address 102, so on and so forth. All right. So when I say S is equal to hello, like this, what it's actually doing is it's well, you'll see the full line of code here. Let me do it this way. We'll say char pointer S is equal to malloc. I'm going to put the math in here, even though we just saw that char, the size of a char is 1 byte. So anything times 1 will be that anything, but I'm still going to explicitly write it here. So I want to be able to hold, what I'm going to do is I'm going to say, look, I want to be able to support a string up to 100 characters. Okay, because I might use this variable to hold different strings, right? I'm not necessarily saying definitely be wasteful, but I'm creating a variable capable of holding a string, a char pointer, which is the historic way strings were stored in C and C++, and understanding pointers is vital for what we're going to be doing here. So that's why I'm purposely going old school with this, because we're going to be doing plenty of things just like this with like integers and things like that. So I want to allocate some memory. Malloc. That's what malloc does, is it allocates memory. How much memory do I want to allocate? Well, let's see, I'm gonna keep my example correct. So we're gonna go ahead and say this is 10 times size of char. All right, and what that's going to do, I don't want to write as much. 7. All right, so it just so happens that I know 7's a little bit limiting for that to being the maximum size of a string that we're going to hold in our example here, but it's bigger than hello, so it'll still show our example. Okay, so this will allocate some memory. So initially, all it does is it creates this structure here without the hello in it. It creates, it goes out and finds memory somewhere in the operating system that is big enough. It's got to be contiguous memory, memory right next to each other. That's big enough to hold this many of these guys. Make sense? If you want to see the Java equivalent to this, in Java, we would have said char array S is equal to new char array 7. That's the equivalent line in Java. The new keyword goes and gets us memory. Malloc goes and gets us memory. All right, make sense? Then I'm going to say S is equal to hello. Now, what gets returned by this function malloc? Malloc returns a memory address. That's what malloc does, is it returns a memory address. So I have a variable named S here. Chat. All right, so we have a variable named S here, and S has a value. The value of S is not a string, even though it looks like I put a string inside of S. The value of S is the base address of this string. So in this example, S has a value of 100, which is said to point to the beginning of where this string lives in memory. Make sense? Okay, so S gets its value up here, so I'm first creating a bucket for holding a string. So I want to create a big enough thing to hold 7 chars and give me some memory for holding that. This little asterisk thing here says pointer. I have a char pointer. Okay, the asterisk says the type of this variable is a pointer. And what kind of values do pointers hold? An int holds a number, right? A char holds a number. Pointers hold memory addresses. That's the job of a pointer, is to hold a memory address. All right, so S will hold a memory address, and that memory address is said to point to the base address of this string, in our case here, in memory, or our character array in memory. All right, now when I say S is equal to a hello here, what it does is it goes to the base address of S, and it starts putting one character at a time into memory, into that contiguous memory. And because it's a string literal over here, it terminates that string with the string termination character, which is a \0. Let me just write that here real quick. Okay, what was the question? You had a question? You did? Not anymore?
So you're expecting the size.
Yeah, but don't focus on that right now. Correct. Java allocates new memory. Well, you just like Java, you'd have to allocate new memory. Java does allocate new memory. It's not different. Yeah, we're just doing it manually here, where Java did it automatically. Correct, because you need to have enough memory to hold the string that you want to hold, and it's got to be contiguous. It has to be right next to each other in memory. All right, so even though I have a container that can hold 7 total characters in memory here, I'm actually only using 6 buckets of it. 5 buckets for the contents of hello, and then that one last bucket for the string termination character. All right, and let me show you how this works. Let's go out here to C++. We'll just say working with char pointers. And it's standard lib I need to bring in here. So I need to do include standard lib.h. I think it's just I think it's .h, not just standard lib. Is that something from the C days? All right, and then we're going to go ahead and we're going to say char pointer s is equal to. I didn't. Oh, you have a variable named s. Okay. Char pointer s is equal to malloc 7 times size of char. All right. Now, technically, this is going to give us something called a void pointer. Probably is the error it's going to tell us here. So this is going to give us a void pointer. So you would need to typecast it to a char pointer. Okay. Now, the reality is that since we put char pointer out here, it already knows that we want to deal with the size of char here. So you actually wouldn't need to put that in there. Let me keep it in there for now just to really drive that point home. That this is building enough memory to hold 7 of these guys. But I don't want to confuse that with this. I'm missing a parenthesis there. Oh, I said char pointer. There we go. These 2 lines do not give you the same amount of memory. This line will give you enough memory to hold 50 integers. And an integer is 32 bits. Okay, or 4 bytes. So this will give me 200 bytes of memory. This guy down here, since the size of int is 4, this is going to give me 4 times 500, 4 times 50, which is 200, times the size of bytes. So it'll actually give a size of int, so it'll actually give me 800 total bytes. So what I'm getting at here is that this part here is not something we write. Typically, we're allowed to write it, but this will grab us more memory than this one will. This one allows us to hold 50 integers. This one will give us a number, the ability to hold 200 integers. Because this math we're doing right here gets done for us when we use malloc. Go ahead. Yes, except size of char is 1. So 7 times 1 is always 7. It's still 7. Yeah, it just happens to be that the size. Yeah. Okay, so in any case, we have S here, and let me just, I'm going to comment these out. So we're going to go ahead then and say, we're going to say S is equal to, I think I used the capital H in there, right? Is equal to hello, and then I'll say C out S and L. Now S is a char pointer. That's the kind of value that we're displaying. So we're asking C out to resolve S, which is a char pointer. Oh, that's just a warning because it's telling me that now we have strings that we can do this with, but warning doesn't mean an error. We're fine. So there's my hello. Okay, but now when it printed that out, what did it do? It went into S, and what it actually did is it said S is some memory address. Okay, so if I were to print out the value of S as a, I'll show you. If I print out the value of S as a char pointer, I think they should give me the memory address. Sorry. See if it was a void pointer maybe, and then I'll let me get it. There we go. So there's the memory address By making it a void pointer, I'm saying, look, this is a generic pointer. Don't try to do anything fancy to it. Because char pointers are still strings, right? And it's the cout function's resolving it as a string and saying, oh, well, yeah, it was already a char pointer. You want to cast it to a char pointer? Okay. You can go ahead and do that. You didn't actually change anything. Now I've turned it into a void pointer. So I just said, look, don't try to do anything special with this. Give me its memory address. So this is the actual memory address that we got as a response from the malloc function. All right. Now, in my example in the slides, it's a much less scary number. I assume that we got the memory address 100. Okay. So S actually holds the number 100, which points to the very beginning of this string. So that means if I were to print out the char that lives at that location, go back in here. So that'll print out the memory address. This will print out the whole string. But what if I say I want to print out the char that lives there? Go to memory address 8. Tell me the character that lives there. I might actually have to do this with pointer. Okay, that's fine. Let me make sure this works and then I'll explain what it is. There's my H. Star S says, give me the value that lives at this address. Okay. What if I say star S plus 2? One, 2. That'll give you the L. That's like saying char at bucket 2. So there's my L. So I'm walking through memory manually.
I have a question.
Go ahead.
Would you be able to print out, or like, I'm not asking if you are like actually able to, but would you be able to show what happens if you print out like void pointer S plus 2?
So you want this?
Yes, please.
Okay.
I'm just what
Yep.
the memory address of.
So what do you think it's going to give us?
It's going to give us the memory address of the first L in hello. I'm just curious what it looks like.
Yep. And what it'll look like, it'll look like whatever this hexadecimal value is, plus 2. That's what it's going to end up looking like, because it is contiguous memory. It's in a row. So 627C, 627E.
What's that 0x at the beginning? That was making me.
That's it's hexadecimal.
Okay.
So whenever a number is written like that, if you see a 0x before it, that is our way of telling us this is a hexadecimal value.
Okay, thank you.
But the actual value is this guy. Good. Yes. And this whole class is going to be about that, because this class we're going to start probably next class or maybe the class after, start dealing with linear linked data structures like a linked list, where char pointers are our way of kind of dipping our toe into this, because we're kind of saying, well, we can do it as a string or we can do it as walking memory 1 byte at a time. But once we get to, for instance, node pointers, so I might create a class called a node, and I keep the address of a node, and I want one node to point to another node, which points to another node, and we start walking through memory. So we need to be very, very comfortable working with pointer syntax and understand what's actually happening. All right, so let's look at this a little bit more now. So if I want to get bucket 2 of this guy, I can add to, well, let's see, let's do bucket 4. So I can either say, give me the value that lives at bucket 4, or I can say, give me bucket 4. These two do the same thing. This guy is syntactic sugar for actually doing pointer math. By pointer math, I'm saying S is a memory address. I'm adding 4 to that memory address, which will walk it 4 bytes later. And then I'm saying, give me the value that lives there. That's what the asterisk beforehand means. So there's our O. All right, now to Emily's point, I'm pretty sure the reason she was asking this question is she's like, well, why would anybody write this when you could just write this, right? It's because people think you're better when you do this. You just look cool. No. A modern developer might write it like this, and that's perfectly acceptable. But a modern developer who didn't learn what's happening under the hood wouldn't understand that this is actually syntactic sugar for that, walking through memory. And if you don't understand memory, linked data structures are going to be very, very difficult, okay? Because the whole purpose of what we're doing in here this semester is dealing with things that are strewn about in memory, and we need to get from one element to another element to another element because there's no guarantee they're sitting next to each other in contiguous memory. Right now, our strings are stored in contiguous memory. So this guy is contiguous memory, memory in a row. This is what malloc gave us. Malloc in this case gave us enough memory next to each other to hold this many of these guys. That make sense? Okay, but the presumption is it's right next to each other. So in order to walk through memory, I can do pointer math here, which looks intimidating, but all it is doing math. It's saying, you start at memory address 100, you want to get to the 4th bucket, you add 4 to it, now we're at memory address 104. Bucket 4 is at 104, bucket 5 is at 105, so on and so forth. All right, now we're going to break it. I've mentioned that cout looks for this string termination character to know when to finish, right? So I'm going to go ahead and overwrite that string termination character with another character, and we're going to see what happens. So I'll go ahead and I'm going to say S plus, what is it, 6? Is equal to a B. So notice here that we now have a segmentation fault. Get used to those. You're going to run into them this semester. All right. Whenever you see segmentation fault, what does that effectively mean? something pretty similar to array index out of bounds from Java. We walked off our allotted memory. Okay, because what were we trying to do here? Well, cout was saying, you've given me a string. No problem. I'll just start printing out character after character after character until I finally hit a \0. But what happened here? We never hit a \0 because I overwrote the \0 that was automatically put in there with a B. Now I can fix this up and I can go and say, I know I happen to have one extra little bucket here, right? So we'll say +7 is a \0. Oh, hold on. It's not bucket 7. It is, I made it so this should be bucket 5. This should be bucket 6. So here, just to show you the deal here, that we still have the segmentation error. I'm overwriting bucket 5, which used to be the \0 here. So there's no \0. One of two things is going to happen. It might be smart and say, I'll just print to the end of the memory you've requested, or it might be like original C and C++, where it'll run out of memory and give you a segmentation issue. Yeah, segmentation issue. So I'll go ahead and I'll toss in that \0 at our very last bucket, the last legal bucket. This is memory that belongs to us. Ay, ay, ay. Allowed. I'm using bad syntax there. Won't let me overwrite it. Well, I'll look into. I'm sure it's a stupid syntax thing that I'm messing up here, because I'm saying S at bucket 5. I'm trying to set it equal to B, and I think it's actually this line that's giving the segmentation error. It's saying you can't write to this directly, so it might just be protecting the memory. I'll spend a couple minutes in my office and figure it out. All right, so any questions about this memory stuff we've been talking about at this point? So what I'd encourage you to do for Thursday is take what we did here and go and kind of start playing with the C++ compiler, seeing what doesn't work, seeing what works, fill it up with strings, that kind of stuff. And then we're gonna keep going from here on Thursday. Sound good? All right, I will see everybody on Thursday.
I have a quick question, not about programming or anything.